Okay, so today is the equivariant K theory of the Steinberg variety. So what the goal is to prove that the affine Hecke algebra is isomorphic to the G times C star equivariant K theory of the Steinberg variety. And I don't think that I will quite get through the full proof today. I'd hope that we would just have one lecture on this, but it looks like it's going to need a little bit more detail. But we'll get close to it. And then what we'll see, as I tried to explain last time, is that the main kind of crucial idea is to show that both of these things act on the same vector space via the same operators. So it's a rather bizarre proof. It's a rather bizarre proof that two algebras are the same. You know, you don't really construct an isomorphism. You show that they generate the same subalgebra inside the endomorphisms of some big vector space. And let me just comment. So this is some part of Langlands duality, and there are about 10 different proofs of things related to some kind of Langlands-like correspondence that involve, you have objects on both sides and then you match them inside some bigger object in the center, but you don't actually construct a direct relation between them. And so this is another instance of this. So it might seem a little bit unsettling, but it's also something that seems to happen a lot when you try to establish Langlands type dualities. Okay. As I'm sure you're aware, there's notes on the website. And basically what I'm following is the paper of Kazhdan and Lusztig, proof of Deligne-Langlands conjectures for Hecke algebras. It's about paper from about 1980. Chris and Ginzburg's book, Representation Theory and Complex Geometry. It's a fantastic book. And also there's some notes of Anthony Henderson that I'll ask if I can put them on the webpage. These are called Notes on Affine Hecke Algebras and K Theory. And I just want to, and the other point today is that I don't see any kind of point in rushing through this stuff. And so at some point I structured the whole lecture to get to the end today of this isomorphism, but then I thought, what's the point? Let's take our time. We have plenty more Fridays to go. So I slowed down a little. So we've discussed this to some extent before. So if X is a scheme, so this is a scheme, we can associate to this the K theory, so Ki of X, and so these are the K groups of our scheme, and K0 of X, this is the Grothendieck group of perfect complexes. There's bounded complexes of vector bundles. And if we have a group acting, then we can consider the equivariant K theory groups. And this is the Grothendieck group of G equivariant. Perfect complexes. And roughly, so let me tell the story verbally a little bit of K theory. So the K groups were invented by Grothendieck to state the Grothendieck-Riemann-Roch theorem. And the idea of then of K groups was taken up by Atiyah and Herzebruch, and they defined topological K theory. And topological K theory was enormously powerful. So you could think about, for example, topological K theory is linked up with the Atiyah-Singer index theorem. And you can think about topological K theory as being something a bit like cohomology, but which is sometimes more geometric. So it's more directly related to questions in geometry, but it still has a flavor of something like cohomology. And so this was extremely useful in solving fundamental questions in algebraic topology. So a classic example of this is Adam's solution of the so-called vector fields on spheres problem, which is a very fundamental problem in algebraic topology that was solved by a K theory. And then my understanding is that people realized that these K groups would also be extremely powerful in algebra. And people were able to write down what was, for example, the first K theory or even the second K theory of a ring. But there was no unified approach to it until Quillen came along and he defined the higher K groups of a ring. And you can think about this a little bit as analogous to cohomology. So when we first do a course in algebraic topology, we learn the definition of homology, and we think that homology is chains. But then quickly you realize that you only need certain formal properties, and then you can build the theory based on formal properties. And then a working algebraic topologist often doesn't think in terms of chains, doesn't think in terms of the original definition. And something similar happens with K theory. However, the original definition is much more complicated. So it was so complicated that it took extremely smart people kind of 20 years to come up with even the definition. And then establishing these basic properties like excision and long exact sequences was extremely tough. So Quillen was able to establish it for smooth varieties, but there was this big open problem for a long time to establish it for singular varieties. And I just want to read to you from the introduction of this beautiful paper, which I meant to okay, so there's this paper by Thomason and Trollbaugh, or I don't know how to say it. I feel like people say Trollborough, but that has nothing to do with the way it's pronounced. So there's this, so for K theory, this paper of Thomason. Quillen papers and Thomas and Trollbaugh are wonderful. And I just want to read to you two inspiring paragraphs from the introduction to the Thomason and Trollbaugh paper. So this was published in a volume in honor of Grothendieck. I think roughly around the time that Grothendieck had left mathematics. And they write at the end of a brief introduction, of course, Grothendieck's ideas completely pervade modern mathematics, and it would be a hopeless task to isolate and acknowledge all intellectual debts to him. But we hope our case illustrates that despite their widespread influence and nearly 2 decades after Grothendieck's withdrawal from public mathematical life, many of Grothendieck's ideas are still full of unexhausted potential and will amply repay further development. Remarkably, his by now classic works can still surprise and instruct the serious reader. We dedicate this paper to him with profound admiration. Okay, that's the first paragraph. And the last paragraph of the of this paper is equally famous, and I want to read it to you. So the paper is called, it's by Thomason and Trobrow. So the first author must state that his co-author and close friend, Tom Trobrow, quite intelligent, singularly original, and inordinately generous, killed himself consequent to endogenous depression. 94 days later, in my dream, Tom's simulacrum remarked, the direct limit characterization of perfect complexes show that they extend, just as one extends a coherent sheaf. Awaking with a start, I knew this idea had to be wrong, since some perfect complexes have a non-vanishing K0 obstruction to extension. I had worked on this problem for 3 years and saw this approach to be hopeless. But Tom's simulacrum had been so insistent, I knew he wouldn't let me sleep undisturbed until I had worked out the argument and could point to the gap. This work quickly led to the key results of this paper. To Tom, I could have explained why he must be listed as a co-author. During his lifetime, Tom also pointed out the interesting comparison of the careers of Grothendieck and Newton. For more mundane assistance and useful conversations, I would like to thank Gillet, Grayson, Karoubi, Castle, Levine, Lodi, Nisnevich, Ogle, Sule, Waldhausen, Weibel, and D. Yao. Okay. So, I don't know, it's a really extraordinary paper and it's a really extraordinary introduction, and I recommend you reading it if you get the chance. Okay. So, I just
wanted to make a remark about K theory. So,
sure.
Something that I learned from Greenfield. So the way he described it is that one can also think about K theory as kind of a smart abelianization. So even if you think about the case of a monoid, so when you want to consider the K theory of a monoid, well, first you can abelianize the monoid and then you sort of make it into a group. So it's sort of the smallest possible abelian group that you can map your monoid to. And then you start with a category, symmetric, a monoidal category, and you ask yourself, what is the sort of smallest Picard category to which it acts, to which you map? So Picard is the analog of abelian group in the category world. And then, so if you sort of take this idea far enough, you will sort of come across K theory. That's sort of, and if anybody is interested in sort of seeing this in an informal writing, Justin Noel and I started writing a paper to implement this idea, but we never finished because, anyway, for various reasons, but I've put on a draft on my website of the incomplete paper, which has some, at least the introduction has some informal ideas if somebody's interested.
So just to expand on what Masood is saying, that so when we form the K group, we form these symbols and we kind of add, you know, the Grothendieck group formally adds inverses to objects. You know, you can subtract an object in the K theory, but you can't subtract an object in an abelian category. And that operation, when you do it formally enough, in a homotopical enough way, produces K theory, which was
so
okay.
You have to work in infinity category setting to actually get something topological. But anyway. So.
Okay, so and roughly, so if we have a scheme, and we have an open set, and Y, which is, this is open. So we can consider perfect complexes on X supported on Y, and the K theory of that gives us Ki of, in the Thomas and Trobra paper, this is denoted X on Y. There's perfect complexes on X. And then you can, of course, restrict to an open. Okay. And so this is an exact sequence, except, so this is that K0 of X to K0 of U might not be onto. Okay. But it's for singular X. And you can think about this long exact sequence as being like the fundamental thing, like the long exact sequence of cohomology. But now this long exact sequence took about 20 years after the birth of K theory to get proved in full generality, and that's what this Thomason and Trobel paper does. Okay, and I will allow myself in this lecture and the next one just to assert that certain long exact sequences are certain short exact sequences are short exact sequences without telling you why. Okay. I've lost my lecture notes somehow. Okay, so now some examples. So a vector bundle, a G-equivariant vector bundle on a point is the same thing as a algebraic representation of a group. And so the that's very important for us. And I'll just write K for K0. Okay. So I won't care about the higher K groups, except when at some points I'll say certain sequences are exact and I won't tell you why. Kg of a point is the same thing as Rg is the same thing as the Grothendieck group. Of this finite dimensional algebraic representations. And B, I just wanted to go through this example in some detail because it's fun. So this is the fact that the K theory of P1 is K x plus or minus 1. Sorry. Z x plus or minus 1 modulo the relation that x minus 1 squared is 0. So why is this the case? So we know that every vector bundle, for example, in Tom's course, we've seen that every vector bundle on P1 is a sum of line bundles. And what we're taking is the Grothendieck group of the exact category of vector bundles on P1, if you will. And so we have a surjection onto the K theory of P1 that sends x to the m to the class of O of m. And this implies that this is surjective. And now we have, when you first learn about what the tautological line bundle is on P1, you say it's the line bundle whose fiber over a line is points in that line. Yeah. So another way of saying that is on P1, we have the trivial two-dimensional vector bundle. And then we have the tautological subbundle, and the quotient of this is O of 1. So that tells us that x inverse plus 2 plus x maps to 0 over here, but we can rewrite this as saying that x minus 1. Yeah. So of course, this sequence we can this sequence here we can tensor with O of 1 to get O goes to O of 1 goes to O of 2, and this is an exact sequence. So the class of this minus the class of this minus the class of this goes to 0, which is exactly saying that this is 0. Okay. So so that says that we definitely have a map here. And the fact that this is an isomorphism follows from the following claim, is that is freely generated by the structure sheaf and O of 1. And we've seen above that these generate so enough to show that they're linearly independent.
Sorry, Geordie, shouldn't it be x to the minus 1 minus 2 plus x?
Yep. Thanks a lot. You know, so this is like very, very simple example, but it's really fun to go through these simple examples carefully, yeah? So let's prove this in two different ways. Is that there's K theory carries a kind of intersection form. So which is just given by Fg is the Euler characteristic, the holomorphic Euler characteristic of F tensor G. And what's this for P1? We have O of 1, O of 1. So if we tensor O with O, we get O. What's its global sections? So we need to know its cohomologies in all degrees, but O has no higher cohomology on P1. So we get a 1 here. O of 1 has a two-dimensional H0 and no higher cohomology. So we get a 2 and a 2. And when we tensor O of 1 with O of 1, we get O of 2 that has a three-dimensional space of sections and no higher cohomology. So we get a 3 here. And the fact that the determinant is 3 minus 4 is minus 1 implies that okay. Second proof is that in Tom's course, we saw that dB of co P1 is equivalent to dB of rep and moreover O of 1, O goes to the representation which is K0 and O of 1 goes to 0. Okay, this was remember that we've discussed this. This is a tilting bundle. Okay, but K0 of a finite dimensional algebra is freely generated by the classes of the simples. Okay, and these are precisely the two simple representations of this quiver. The reason that I'm giving this approach is that it illustrates the fact that often derived equivalences give you interesting facts about K theory. So you might have a derived equivalence that gives you two very different bases, for example, in K theory. And here we're saying that it's maybe not so obvious over this side that O and O of 1 are a basis, but over this side, it's patently clear. And just to continue the examples for a little bit longer, is that all good?
Geordie?
Yes?
In that second proof, where is the hidden role of the intersection form?
I would say it's not there at all. Would be my feeling. So this the intersection form in the first proof comes from the monoidal structure on coherent sheaves, but on the other side of this derived equivalence, this is not a monoidal equivalence. So but maybe, yeah, maybe this still is the Euler form. It's possible this still is the Euler form. So there's something called the Euler form, which is basically, yes. Anyway, so good question. I don't know. It may or may not be hidden.
It's surprising how different are both proofs.
Yeah.
And where are we using properness?
Oh, just that this Euler characteristic is a finite number. You know, you want this to be the Euler characteristic of a complex with bounded and finite dimensional cohomology. Okay, so if we have a proper map, this induces F star between the K groups. And note that this is not monoidal. And I mean, I've been through before the fact that you have various functors. So for example, if you have a flat map, then you have pullback, etc. And just if we have then this induces the map on K theory so this is Z, and this sends O of M to the Euler characteristic of its global sections. So this goes to M plus 1. And notice that, I mean, this is, we saw before, x plus or minus 1 modulo. And this indeed does go to 0 under this map, which is reassuring. And B, I'm just doing these because we'll do quite a lot of P1 later on, or tomorrow. So not tomorrow, in the next week. So if we have B being the upper triangular matrices inside SL2, then the equivariant K theory of a point is simply the characters of B, which is Z, and the Z x plus or minus 1, and the G equivariant K theory of P1. So this is the same thing as the G equivariant K theory of G mod B, and that's the same thing as the B equivariant K theory of a point. So this is this fundamental equivalence between B equivariant so B equivariant things on a space are the same thing as G equivariant things on G times on the balanced product of that. So if I have H a subgroup in G, then coherent sheaves on X is equivalent to coherent sheaves on G times H X. And in this case, G times over B with a point is the same thing as G mod B. So this is the same thing as Z. Okay, and so now we can pull back to KB of P1 and then push forward to a point, KB of a point, and this map sends O of m to x to the m minus x to the minus m minus 2 on 1 minus x minus 2 inside here. And this is the Weil character formula. Okay, so are there any questions?
Yeah, so what is the punchline here is that the Weil character formula can be understood as a map from equivariant K theory of G mod B to equivariant K theory of point in general, like,
Yes.
and you chase through what happens to a character of an irreducible G representation, and you get some expression for it in the equivariant K theory of point, and that's the Weil character formula expression.
Exactly. Yeah, and now you can take this further and say, like, how do you actually work this out? You know, like here, I'm just saying I know what the characters of the of O of m on P1 are as T modules or as B modules. But probably, but now you can say, like, imagine I have a more complicated group. How do you actually work this out? And then you can use, for example, Grothendieck, Riemann, Roch to rededuce the Weil character formula, or you can explain the Damasio character formula very naturally in this language, etc.
Actually,
But I won't. Yes.
should that be ZXB? The group algebra. XB is the character group. Of
Yes.
then it should be Z. Okay.
Thank you. Okay. So now we go to Steinberg. So I've been through a lot of this stuff before. So we take G, B, T, the characters of T, W, F, the finite Weil group, and I also want the affine Weil group. Now this is associated to the dual root system. Okay, and this is basically to avoid too many Langlands duals below. So I could start with a root system and do everything, but then whenever I'm on the side, on the coherent side of these equivalences, I'd have to write checks everywhere and I'd go crazy. So I'm just not, I don't want to do that. And so we have the Lie algebra of G. And inside this we have the nilpotent cone. And now the important, and we also have B, which is G mod B, the flag variety. And so the important objects that we need are the Springer resolution. So this is pairs X, B, where and I've explained in previous lectures why this is canonically isomorphic to the cotangent bundle of the flag variety. And we have the Steinberg variety, which is n, the fiber product of n with itself over n tilde. So this is pairs xb, b prime, such that x is in b and x is in b prime. And this is kind of extremely important for visualizing this. So I'll go over this again in the example of SL2, but this is what I've called in previous lectures the conormal space to the G action on B times B. Okay. So we'll see this in the example of SL2 in a second. And I just want to emphasize that this has been discussed in detail in previous lectures. So this is called Steinberg variety. So just let's get a very clear picture of what this looks like for SL2. So firstly, we can draw, so B is P1. So B times B looks like so we have a P1 in this direction and P1 in this direction. And so if we're allowed to, so we can think about this as pairs of points in P1. And so SL2 has two orbits on that space, namely the set where the points are equal and the set where they differ. So we have inside here, we have the diagonal. And then we have Y. So maybe and then we have the Y, which is P1 times P1 without this diagonal. Now, what the conormal space means is that we imagine kind of normal vectors to each of the orbits. So here the orbit is dense, and so there's no normal vectors. Whereas here you imagine that there's a one-dimensional space of normal vectors sticking out. So the Steinberg variety is the conormal space of the diagonal inside P1 times P1, union the conormal space, so disjoint union, the conormal space to Y inside P1 times P1. Now, it's a beautiful thing that if you take any space, cross it with itself, and take the conormal to the diagonal, you get the cotangent bundle. So this is the cotangent bundle of P1. And this, because this is a dense orbit, is simply Y. So roughly speaking, you can think about this as being, here's an attempted picture of the here's P1, which is the diagonal, and here's T star P1. And this is union with P1 times P1. And this is glued along the diagonal is P1. Okay, so it has two components. And so remember that the Steinberg variety is also, the Steinberg variety is n tilde times over n tilde. And inside any such space, you always have the boring bit, which is just, it's just the copy of n tilde, which is n tilde in both, like n. That's clearly something in the fiber product. And so that gives you a kind of boring component, and it's probably not too sacrilegious to say that this is the boring bit, the kind of easy bit. And this is the tricky bit. So for example, we'll see in a second that under this Kazhdan and Lusztig isomorphism, the lattice part in the Bernstein presentation just corresponds to line bundles here, whereas the generator corresponds to something, the generator corresponding to the finite Hecke algebra corresponds to an interesting sheaf here. Okay, so yeah, and I just want to quickly say that G times C star acts on the Steinberg via GZ of XB B prime is, so it scales the X, Z to some power G X, GB prime. And that some power, embarrassingly, I wanted to look back in my notes later because I'll know later what that power should be, but let me not specify it at the moment. And so this is this acts via scaling here. The C star acts via scaling here, and it acts trivially here. Okay. And then G acts as it does on the cotangent bundle here, and as it does on a product of P1 by itself with itself here. So let us have a 7-minute break, and I will start again at, or 8-minute break, start again at 5 past. Okay, I'll continue. Okay, so this is our picture of the Steinberg for SL2. So I just wanted to remind you about the algebra structure. I'm sorry if this is sounding like a broken record, but it's a little while since we've done this. The convolution product. So we can look at this triple product, and this has a number of different, so remember the Steinberg is n tilde tensor, or fiber product over n with n tilde. So this has the first and second projections, the second and third projections, and the first and third projection. And also notice, and this is really important to actually do calculations, is that this sits inside, and this is smooth. So in the example of SL2, we saw that the Steinberg variety is reducible and the components are smooth. But in general, this will not be the case. So it'll be reducible, there'll be components indexed by W, and the components won't be smooth. And so when we do something like a tensor product on the Steinberg of coherent cheese on Steinberg variety, what we really mean is that we view the Steinberg variety as sitting inside something smooth and take a tensor product of that smooth. And so the
forget tildes, Geordie.
Thank you. Yeah. And so and we had this product, which is we pull back by the first and second projection, F, take a tensor product with the pullback from the second and third projection of G. We then move this slightly to the right to allow for more space for later on. And then we take the push forward. And I just want to remind you why all of this is okay. So these pullbacks are okay because P1, 2, P1, P2, 3 are smooth. To form this tensor product, to form a tensor product, we need some kind of locally free resolution. And we have that just by this embedding inside a smooth thing where we can form locally free resolution. So this is by embedding smooth variety. So that comes from here. And this is okay. So this projection map is not, this P13 map is not proper, but what you can check is that it's proper on the support of this tensor product. Okay, because P13 is proper when restricted of okay. And you can think about this in previous lectures I tried to explain why you can think about this as some analog of matrix multiplication. Some kind of, so if if we imagine the nilpotent cone is a point and n tilde is the number of points, then f and g become coherent sheaves on the product of a finite set with itself, which you can see as being a categorification of a matrix. And what we're doing here is that we're multiplying matrices. So this gives an associative algebra. And I also want to recall, so basically given any G invariant closed subset of the nilpotent cone, if you pull it back, then it's the K theory of this subset inside the Springer resolution becomes a module over this algebra. I want to do the simplest case of that where I take the nilpotent cone itself. So the module structure. On K G times C star of the cotangent bundle. So here we have and then we define F. So this is in the G times C star equivariant K theory of the Steinberg. So this is in here. What do we do now? Well, we pull back G. So now we have something that lives up here. We take a tensor product with F. And we push forward. Okay. And so this gives the module structure. But you could also do this for other subsets. So another very important case would be to take the inverse image of 0. So then we get the equivariant K theory of the flag variety. And then a very similar formula will give you a module structure on this.
Geordie, can I ask a quick question?
Sure.
The associative algebra, the unit, is that like a constant sheaf on a diagonal?
Exactly. So, yeah, so you think about, so we have this diagonal inside the Steinberg. This is the kind of easy bit. And in this analogy, when I was talking about the square of a set with itself, the diagonal is precisely the kind of thing that supports diagonal matrices. So, yeah, this is an extremely useful aside, which is that KG, so let's call this n diagonal, C star of n diagonal inside K blah of Steinberg, should be thought of diagonal matrices. In particular, the unit is the structure sheaf of this diagonal. And moreover, when, in the previous slide, so I'm just going to move slides for a second. So here's the kind of diagonal matrix bit, and this is the bit that supports the lattice part of the Bernstein presentation, which is the kind of easy bit inside the Bernstein presentation. So the unit would live just on here, and off diagonal tricky business lives over here. Okay.
So you said that P13 is not proper, but it's proper on the support of anything of this form P1 over 2 star F tensor.
So note that P1, 1, 2 upper star of F is not upper star of anything, it's upper star of something supported. So the general scheme for this convolution business is I have something inside a fiber product and something inside another fiber product. So I have let's say I have a fiber product of A and B and C. And I have something inside of that, and then I can define the composition to be, I take the product of this inside the fiber product of A times B and B times C, and I intersect and then project to A times C. And the condition for when I have such a product is when that map is proper. So basically, the statement is that anything supported on Steinberg, so if I consider the pullback of Steinberg in the first factor, the pullback of Steinberg by P12, and intersect it with the pullback of Steinberg under P23, then the image of that map under P13, so P13 restricted to that intersection is proper.
I guess I was just wondering, like, if you take specifically F and G to be the structure sheaf, then the pullbacks would still be the structure sheaves.
Mm-hmm.
And the intersection is not everything.
The intersection is everything. So yes, so this has to be proper on that. Oh, so you're saying yeah, I think yeah, you're right. P13 is just proper.
Okay, yeah, that makes sense. Thanks.
Yeah, because so maybe so this is the space of X, B, B prime, B double prime, mapping down to something like X, B, B double prime. And so the fiber over a given X is those B prime containing X, which is a Springer fiber. So it's a closed sub-variety inside a flag variety. So it's proper.
Oh, thanks.
Yeah. Sorry. Yeah, so thanks a lot for the question. So that makes that explanation a bit easier. Okay. So now I just want to explain what this equivariant K theory looks like as a I want to explain what these two, the equivariant K theory of the Steinberg and this guy look like as vector spaces, and then we'll explore their module structure. So vector space structure. So of n tilde is the same thing. So one of the black boxes from K theory that I won't explain is that if I have a vector bundle on something, an equivariant vector bundle on something, it's kind of homotopic to the base space. And so that you pull back always gives you an isomorphism in K theory. So n tilde is a vector bundle on K on the base, B, and B is G mod B. So this is the same thing as the B times C star equivariant K theory of a point, which is just the representation ring. So I'll write this for the representation ring of C star, and then I take the characters of B, which are the same thing as the characters of T. For the Steinberg, it's a little bit more complicated. So what we'll use is the filtration via, so we have a filtration via closures of. Okay, so G orbits on B times B are the same thing as B orbits on B, and here we have the Bruchard decomposition, which gives us a filtration of the flag variety with successive differences affine spaces. So each Z I without Z I minus 1 is isomorphic to the G orbit of xi b b for some xi. And that's isomorphic to a balanced product over B of a Bruchard cell. And I want to call that x sub xi. So this is a kind of a Bruchard cell. So this, and remember the Steinberg variety is the conormal space to the G orbits on B times B. And so that tells us that the irreducible components of the Steinberg variety are indexed by the same set as our Bruchard cells. So we get, so this induces a filtration. Empty set equals Z minus 1 tilde. The Steinberg variety such that Zi take away Zi minus 1 is isomorphic to the conormal bundle to X B times B. That's a B times B, not a B XB. And so I just want to call this TXI star. So this is the conormal bundle to the orbit determined by XI inside B times B.
Your question.
Say again?
Sorry, trivial question. Is there some reason you're not using the index 0?
I guess I wanted, why did I want this to be? Yeah, no idea. I guess I can't, yeah. No idea. No idea. Yeah. I mean, I probably what was going through my head was the length of the identity element is 0. And so I want the first thing to be. And then, so it should be believable, so that the G times C star equivariant K theory of this TXI star. So TXI star is a vector bundle over, so this should be the same thing as G times C star of XXI, which should be the same thing as the B times C star equivariant K theory of BXI B mod B. But now again, this is an affine space, so this should just be the K B times C star equivariant K theory of a point. And so the moral is that from each of these pieces in this filtration, we get something that looks like this, and then a black box, which is basically that the K theory behaves very well with affine stratifications, is that the G times C equivariant K theory of the Steinberg is a direct sum over X in W of the times the structure sheaf of TXI star. Sorry. Okay, so the components of the Steinberg variety are naturally indexed by orbits of G on B times B. These orbits are classified by W. And so for each of these W, we have a conormal bundle that gives us a component of the Steinberg variety. And these freely generate the equivariant K theory over the equivariant K theory of a B times C star equivariant K theory of a point. So I'll just wait for 3 seconds and then go back a slide.
Excuse me. Is there any conditions in set 1 for the filtration?
So this should be, so there's a unique closed G orbit on B times B, which is the diagonal. And so Z1 has to be the diagonal.
Mm-hmm.
And then I'm allowed, and then I'll take all my simple reflections, etc.
So why don't we write Z minus 1 as Z0? Okay.
So just back in this picture up here, so this filtration would have this piece first. So this is the conormal bundle to that diagonal. And then it would have this piece here. And there's two elements of the Weil group here, identity and S. And the claim is that each of these contributes an equal amount to the equivariant K theory. And so we should compare with the fact that the affine Hecke algebra is direct sum X in W of times chi times in the finite. Okay, and these two facts will turn out to be precisely analogous, even though it's certainly not true that this corresponds to this. Alrighty then. So, as I said last time, we're getting to the point where the water is deeper, and so I have to jump around and assume that you can remember more stuff from previous lectures. But one thing that I'll go over now briefly is the Vanstone presentation. So now I don't know if it's useful for me to remind you what the strategy was, but basically what our strategy is going to be is we want to So I'll just recall verbally the strategy again. So we want to show that this and this are isomorphic. And we've seen that this has a natural module, which is the equivariant K theory of the cotangent bundle, which as a vector space looks like this. Now I will introduce a very natural module for the affine Hecke algebra that as a vector space also looks like this. And then we'll work rather hard to show that certain generators here and here act in the same way on this vector space. And then it's not difficult to show that these two algebras are isomorphic. So now I need to introduce in detail the so-called anti-spherical module. Anti-spherical module. So firstly, I want to recall, just remind you briefly of the Vanstone presentation. So H was this is the affine Hecke algebra, so it's an algebra over.
Geordie, can you go back a little bit? So here, the black box is W or WF? Okay.
Thank you. So H is an algebra over, so the Vanstone presentation tells us the affine Hecke algebra is an algebra over Z V V inverse with a kind of finite part. So this is generated by HS for S in SF, and a lattice part generated by theta lambda, where lambda is in these characters from before. And I want to remind you, as per Lin-Wan's comment then, that these are the finite simple reflections. And so this we call the finite part. And this we call the lattice part. So this is just the finite Hecke algebra, and this is just isomorphic to the group algebra over this of a lattice, of this lattice. So we have theta lambda theta gamma equals, whoops. And over this side, we have something like HS squared equals V inverse minus V, HS plus H plus 1. Okay. And the most important relation is the Vanstone relation that tells us how these two subalgebras interact, so if S is S alpha, is a simple reflection, then this is V minus V inverse. Okay, so this is extremely important relation. So in particular, if S fixes lambda, so if lambda is in the hyperplane fixed by S, then there's commute. And there's a really lovely way of rewriting this relation if lambda is 1 away from the reflection hyperplane. So if S of lambda is lambda minus alpha, then there's a beautiful way of rewriting this relation, which I don't think I'll go into. So if you're interested in that, you can look at the notes. So we can rewrite this relation up here as being that HS and this tells us that HF has 2 natural rank 1 modules. The trivial module, where each HS, so this relation here says the eigenvalues of HS should be either minus V or V inverse. And so the analog of the trivial representation is when HS acts as V inverse. And the analog of the sign representation is when HS acts as minus V. And then we get this module M, which is the, actually N, which is the anti-spherical module, which is, H tensored over HF with sign. And we get M, which is H tensored HF with triv. And these are both isomorphic to as modules over the lattice path. So this is and now I really need to work out how generators act in order to match this with something in K theory. And so that's what I'm going to do now. Okay, so this is the most. And I should have said that this looks like a rational function, but it's actually, this is like the thing that appears in the Weyl character formula up to a little shift. Okay, so I think that this, so I need to get these formulas down, and then we'll see how far we get in actually computing in K theory today. Okay, so remember, so we just care about the antispherical module. So the antispherical module was n sine, and sine means that HS acts as, what is it, minus phi. Minus phi. And by abuse, I'll write theta lambda in the antispherical module for the image of theta lambda tensor 1. And so we want to know how HS acts on theta lambda. So it'll be convenient to work out how it acts on S lambda first. So this is, we're using the Vanstone relation. Plus, and then we get but really this means tensor 1, so this thing here, this is equal to minus phi times theta lambda. So I can write this whole term here as minus phi times theta lambda minus theta lambda minus alpha, all over 1 minus theta minus alpha. And so this becomes V theta lambda minus theta S lambda minus theta lambda plus theta lambda minus alpha. So this becomes V theta lambda minus alpha minus theta of S lambda. And I'm not sure how much you know and love Kazhdan and Lusztig theory, but a general principle in Kazhdan and Lusztig theory is that this guy's a bit annoying, this generator. So if we instead take the generator BS, which is HS plus V, i.e. we just add a copy of the identity on it, then this traditionally is the kind of object that acts, for example, as a translation functor in category O or something like that. And so we expect this to act in a simpler way than HS itself. And so I just want to quickly derive how BS acts. And I take this whole expression, and now I add V times theta S lambda. And so what I get is V theta lambda minus alpha plus theta S lambda minus alpha. And this is looking really promising because I can, so I'll just move that over here. And now in red, if I multiply by theta minus alpha outside of here, I can get rid of this and get rid of this. And so my final term becomes v theta minus alpha minus v inverse, all outside of theta lambda minus theta S lambda, all outside of 1 minus theta minus alpha. Okay, this formula is called the de Maistre-Lusztig formula. So these chaps here look like de Maistre operators, which are basically, if I look at G mod B and I want to push forward a line bundle G mod PS, and I want to calculate how that acts in K theory, then those operators are given by these type things. And then I think it kind of came as a surprise to everyone when Lusztig wrote down these operators and show you get an affine Hecke algebra action, because that's rather different from the algebra generated by, for example, de Maistre operators. So maybe I'll try once to explain where this relation, so here we have a relation in algebra, and then I want to do a computation in K theory and show you that a very similar thing takes place. And then maybe it'll be a bit incomprehensible, and then you'll think about it for a bit, and then I'll repeat the same explanation or a mild variant at the start of next class, and then explain in rough terms what the general case looks like, and then we'll move on to categorical considerations. Sound reasonable? Okay, so this, I mean, this formula here shouldn't look too bad. So we take our, so I just want to replace it with, so we can replace lambda by minus lambda easily here, and we get v inverse minus v theta minus alpha. So it just multiplies the right-hand side by -1. That's actually the formula that I want. Okay, so let's try to imagine so for SL2. And now I want to take a slightly different picture of the Steinberg variety. So I want to imagine that this is T star P1. And then here's the Steinberg variety, sits inside T star P1 times T star P1. And it kind of sits as P1 times P1 here, the difficult bit, plus the diagonal from earlier. And what I want to consider is the following line bund, following coherent sheaf. So Q, which is defined to be, what did I want to take? O of 1 on P1 times P1. And we regard this as sitting inside the Steinberg variety. And the question is, what does how does this guy act on K theory? So let's apply the definition. So we take Q so O of so O T star of M is just the pullback of O of M from P1. And so what we do is we tensor Q with P2 pullback of O T star of P1. And then we push forward with so what this does is, so what we're doing is we're pushing back, we're pushing forward O of 1 M minus 1 on P1 times P1. Okay, so one imagines that Q is supported here on this P1 times P1 that we can't see in this picture. But if we tensor with the structure sheaf, so if we tensor O of M on T star of P1 with the structure sheaf on P1, we just get O of M. And so we start with something here, we pull it back to this whole picture and tensor it with something just supported here. And what we ended up is with this sheaf. And now when we push it forward, in the fiber we have a P1, and on that P1 is the bundle O of M. And so what we get is x times x M minus 1 minus x to the minus M plus 1 minus 2, all on 1 minus x to the minus 2. So here I'm applying Weyl's character formula. So I'll go into more detail about this next time, but the crucial thing is that we get this tensored with the structure with the structure sheaf on P1. So when we pull back our line bundle and it's supported all along here, then we tensor with something only supported on P1 times P1. So we've got something supported here. We push it forward and we get something related to Weyl's character formula times the structure sheaf here. And this gives us something like x to the m minus x to the minus m all on 1 minus x to the minus 2 times the class of OP1. Now, to finish this story, so how about I just state that, so this gives us xm minus x to the minus m, 1 minus x minus 2, times what do I get? So I get something that's basically this factor v minus v x to the minus 2. Essentially from a causal resolution of this. Remember, I want to re-express this in terms of vector bundles, which are my generating objects of the. Okay. And so the moral is that this formula here looks very similar to this formula here. Okay, this is the bit coming from Weil's character formula, and this is the bit coming from the causal resolution. So, yeah, so if you're interested in digesting this, have a look at the notes. I will explain this. I'll go through this again briefly at the start of next lecture, and then I'll explain what the general case looks like, but probably not in heaps of detail. And then we'll move on to Arkhipov Bezrukavnikov.
I actually had a question about the notes. There was a intriguing line saying that, like, if you had a modular version of Bezrukavnikov, then you would know everything that we know about modular representation theory. So I was kind of curious, like, what do you mean by that, and also what exactly is the difficulty of the proof in the modular case?
So, for example, if you interpret, so one thing that we would love to know is something called Finkelberg-Merkovich conjecture. So this is the statement that the principal block of representations of an algebraic group are equivalent to perverse sheaves on the affine Grassmannian. And this would follow, if we knew Bezrukavnikov's equivalence, this would basically follow via two different realizations of the spherical module, for example. And so what are the difficulties? So I would say one of the, so the first comment is that Asimo and Pramod and Laura Rida have really thought about, like, they've kind of gone through Roman's proofs and tried to generalize them, so they can really, you know, point at, you know, lemma 4.6 doesn't work with mod P coefficients. But my rough impression is that, so Roman makes a lot of use of kind of arguments from Tanakian formalism. So, like, certain endomorphisms are equivalent to actions of certain elements in the Lie algebra and things like this. And my understanding of it is that kind of when you want to make these statements mod P, the Lie algebra gets replaced with the group, and then suddenly my understanding is that the basic difficulty is the difference, like the Lie algebra and the group are rather close in characteristic 0, but differ much more in characteristic P.
I see. Do you know anything, like, so there's also this derived version of geometric, just the spherical derived Satake, derived equivalence. Like, does that one have any representation theoretic significance, like in the modular case that you?
So that's behind the proof of this so-called Merkovich-Vilonin conjecture. So that's very significant for us. Oh, so just before I forget it, the other thing that drives us totally crazy, and this I have visceral experience with, is the difficulty of taking logs mod P.
Mm-hmm.
So for example, if you look at something like, you know, like a key observation in Roman's work is somehow that, so you're familiar with Gates-Greer central functor?
Yeah.
So it has this nilpotent endomorphism called log of monodromy,
Right.
which is somehow what allows him to lift from G equivariant sheaves on a point to G equivariant sheaves on the Lie algebra.
Uh-huh.
And taking that log of monodromy is just, so we have a, I think, what's the situation? So we have an endomorphism, but we don't know its log of anything. And yeah, so it, like in Bezrukavnikov Yun, so yeah, and this is another place where we really get stuck. So in Bezrukavnikov Yun, so I want to explain in much more detail what Bezrukavnikov Yun do, but what they consider is they look at G mod U mapping to G mod B.
Mm.
And so it's the T torser, and then they look at a completion of the so basically they look at things with unipotent monodromy along the fibers of G mod U to G mod T.
Mm-hmm. And
there's an old argument of Verdier that says that you have some kind of action of the Étale fundamental group of the torus. Like, you know, if you have a sheaf that's monodromic on a torus, then you have an action of the essentially via monodromy of the fundamental group of the torus.
Uh-huh.
And the thing that makes everything work for Bezrukavnikov Yun is the ability to take logs of that monodromy action.
Mm.
And there we have no idea what to do, like totally no idea.
Cool. Because Roman said that he was working on the kind of, along with Simone and Promote, I think, and Arinkin, on like the modular version of the spherical derived equivalence. But I don't know if that, you know, similar has some implication.
The spherical derived, but that's Finkelberg-Merkovich. Yeah, so
that's Finkelberg-Merkovich.
Yeah.
Okay.
Yeah, and as I understand it, they've got a very reasonable and convincing program for doing that, but it still wouldn't like, you know, it's a little bit like the way that Roman originally proved his theorem, is that he got various pieces of the puzzle first and then was able to put enough together to get the full thing. I think it's very, like, you know, you could dream that you could just prove Bezrukavnikov's equivalence via some other means and then deduce all these amazing consequences, but we're certainly not at that stage yet.